So in the previous class we have discussed the decay of this particle, n scalar particle, electron volt. First probability coupling constant of appearing in the interaction between the direct fields and the real scalar field. Now we shall proceed to look at the correction to that matrix element that we have already calculated, and for that we have to go to the third order in perturbation theory. And third order in perturbation theory we call 3. Then that term will be of the following form. Here mean square is 1 in our calculation, and then we will have time order. This one, then this one replaced by x2, and this one replaced by. So this is the S matrix of the third order that we need to look at. And here you see that we have a time order product. This is the time order product of 9 operators, and we need to evaluate that time order product. So let us now concentrate on this term. In this case, we have to write it in longhand. Five. We have to write all the terms, otherwise. Now we have to write all the terms explicitly. So this is the time order product, and here one of the terms here. So this is the thing that I want to get. So one of the terms here, I will just follow in the way in which I have calculated. So here, contract. Now we are using this theorem. And contract this with this, and then the other contraction is this. This one. Psi is 2. So in this time order product, one of the terms will be like this. Now I am just removing the time ordering. So the time order product is equal to this term, but this is only one of the terms. So here we have contracted this thing, and now there will be other terms also, which I shall write it down. Psi bar, psi x1, x1. This is what we have. And here I will contract 5x2 with 5x3 contraction. Other two contractions are this. There are other terms also, but for the time let us focus on these two terms.
Sir,
Yes.
for the first term, why we are not contracting fiber x2 with phi x3? I mean, cyber x2 with psi x3.
Cyber
X2 with psi x3.
Yes, this is a good question. Why have we not contracted that thing? Or you may also ask, uh, yeah. Let's go back. We are saying why have we not contracted these two things? And there must be another operator. See, the way we are contracted, two operators are gone, two operators are gone, six operators are gone. But there must be three operators left, otherwise it will not contribute to the matrix element of the decay process. Okay? Three operators must be left. See, if you apply this theorem, then there will be many terms. See, you may also ask the following question: why have you contracted only three pairs of operators? There, in the mixed theorem, there are many terms. One contraction, all possible permutation. Two contraction, all possible permutation, and so on. But we have not written down those terms because those terms will not contribute in the matrix element. Those terms will be zero. Right? If I just contract one pair, then two operators are gone. But then there are seven more operators left, right? And seven operators, it will not connect. It will not give you a non-vanishing contribution in the matrix element of that decay and electron positron pair. You will not get a contribution because everything will get annihilated. So one contraction terms plus all possible permutations that are there in the Weeks theorem, coming from the Weeks theorem, they are not contributing. So you don't write them. I'm just writing down those terms which will contribute to the decay process. Okay. So let us look at this term, first term, see what it means. So here you have phi x2, x3. So for the time being, let us so let me draw the vertices. X1, x2, x3. And what do we have? We have a contraction of x2 with x3. So x2 with x3 is a propagator from x2 to x3. Then we have psi x1, and that contracts with psi bar x3. Psi x1 contracting with psi and psi bar x1 contracting with psi x2. Okay. So let me draw this. This be x2, this be x3. So x2 to x3, we have a scalar field propagator, and then we have psi bar x1. This contracts with psi x2. So from x1 to x2, you have line, fermionic line, and then we also have psi x1 that contracts with psi bar x3. You may ask one more question, that why are you not contracting psi bar x1 with psi bar x3? What do you think that will be? Anyone? So you can contract psi bar x1 with psi bar x3 also, or psi bar x1 with psi bar x2. Psi bar, they will just give you zero. That does not lead to the propagator. So that is basically nothing but Pauli's exclusion principle. So it will be automatically zero. So x1 to x3, psi bar x1 that contracts with what? Psi x2. So I have written on the line. Now psi x1 that contracts with psi bar x3. So I have given field in that. Okay. And now what you have is phi x1. Phi x1 is free. Okay. And what are the other three things? Psi bar x2, psi x3. What do you think psi bar x2 will be? Psi bar x2, psi x3. So this is the diagram that I discussed in the previous lecture. So we have the three things. These are the three things that you have psi x3. So it was fermionic line at psi x3, and you have psi x2. A psi bar x2 fermionic line will outside. That those are the external lines. But now you have to fix the arrows. How will you fix the arrows? Psi bar x2 will do what? Huh? Psi bar x2 will do what? Psi bar x2 will create an electron, right? Psi bar contains the creation operator of an electron. So you create an electron. And what is?
Now the psi bar also contains annihilation operator.
Psi bar x2. So
It can be both the arrows. I mean,
psi bar x2 is 4 and psi x3. Psi x3, what it does at x3, it is basically the creation, it contains the creation operator of a positron. Is this?
sir.
Ah,
Sir,
yes.
psi x3 also contains the annihilation operator of a positron.
Doesn't matter. Doesn't matter. Doesn't matter.
Okay.
See, at this point, we want this is a particle, this is decaying into these two. There is a scalar particle that is being exchanged, and you should have outgoing particles. What is the outgoing particle that can get created from psi bar x2? Because you see, at this point, particles are. This is your direction of flow of time, right? The particle is coming in direction, and this is the future direction of time. So at this vertex, what is the particle that is getting created from psi bar x2?
Electron.
Psi bar x2 is appearing at this point, right?
Yes, sir.
And particle must be created. What psi bar x2 contains the creation operator of this particle? Is it a positron or electron?
Electron here.
It's electron, therefore it must be electron. And at this point, again particle is getting created. But this point has psi x3. So what is the particle that can be created from psi x3 at this point?
Positron.
So that fixes it. And now these are also quite easy to fix up. You can see that it is psi x1 contracting with psi bar x2. So psi x1 means it is getting created, it's going to arrow will be something like this. See, obviously there will be some arrows here, right? There has to, because there are fermions here. So there has to be an arrow. And this is not a fermionic loop. Fermionic loop you can, okay, you can forget it. But this is not a fermionic loop. This is a loop, but it is not a fermionic loop. What is happening? See carefully. Particle is coming here decay. So there must be arrows. Electron positron pair is getting created.
But
Okay.
sir,
Just a minute. Just a minute. Let me just figure this out. Psi bar x1 and that contracts with psi x2. Okay. So now look at this one. So this propagator is basically psi bar x1 psi x2 contraction, right? You can think on big expansion term. This is psi bar x1 psi x2. At this point, what is the particle that can get created from psi bar x1? Electron. And at this point, psi h2, the electron is coming and getting annihilated from the left hand side of the vertex. The electron is getting created here, and it is getting annihilated at this vertex. So what is the particle that can get annihilated from psi h2? The electron. This must be the electron torque. And similarly, you can show that this other one is basically the contraction of this one. Psi x1 is psi bar x3. So psi x1, what is the particle that can get created on the right hand side from psi x1? Position. And it is getting annihilated at this point. What is the particle that can get annihilated from psi bar x3 at this point? Must be the position. So that is the positron propagator. So that fixes the arrows. Okay. So this diagram is done. So this expression, if I call this expression as A. So this A corresponds to this function diagram. Is this clear? Okay. Someone was asking some question. Okay. Who was asking a question?
Sir, I mean that in the propagator part, the Green's function is symmetric, Feynman Green's function, so we should not put arrow there.
Why not? This is an electron propagator. This is a positron propagator.
But if we interchange the indices x1 and x2, then that will be the same propagator.
Don't think it in such a complicated way. Just think that the particle is coming here and decaying to one electron-positron pair. So if it decays at this point into an electron-positron pair, and there is an exchange of a scalar particle at this vertex, then there must be arrows here. Because it's an electron-positron pair.
Okay.
If you don't put any arrow here, then how do you distinguish which one is an electron and which one is a positron? Because if you remember the tree diagram had an arrow like this. This is the vertex. From the tree, you got from the first order term, you got the vertex of the cube. See, you like, if you don't want to put arrow, it doesn't mean anything. If you like, you can put. If you don't like, you don't put. If you are comfortable without putting arrow, then it is fine. Up to you. But if you are comfortable, for example, I am comfortable in putting the arrows because I can understand it physically. Because at this point it is decaying electron position. And it is going in this direction. And from this direction again it is going in this direction. This direction, this direction. So intuitively I have a better feeling. I don't know why you are not having that feeling. This gives me a better intuitive feeling by putting the arrows inside the loop. And moreover, this is not a fermionic loop. So arrows really make sense. At least for this diagram, it is making sense. Anyway, if you are not comfortable in putting the arrows in the propagators, then you may proceed. But it is up to you. You must, at least, if I do the thing, I will put the arrows. Anyway, so let us call this as B. See, you are saying that this is symmetric in x1 and x2. So if it is symmetric,
Yeah, that's fine.
it's the same thing. But this diagram is the topologically same as the other diagram that I drew earlier. It's the same thing. So why will you not put arrows? Is it clear now?
Yes, sir.
Okay, good. So let us now look at the second diagram. here you will see that once again x2 to x3. So this diagram, x1, x2.
Can you change the board, please?
I will change the, yes. So let me zoom so that you can see the full code. So x1, x2, x3, and this case x2 to x3 is once again a propagator, real scalar shift propagator, and that x3, you have a psi x3 which is free, psi x3. So psi x3 at free means x3 particles are getting created. So psi x3 means positron is getting created, right? And if there is a positron that is getting created here, there must be an electron. So there must be a psi bar x3 also. So there you see psi bar x3 is there. So electron positron is getting created, it's fine. And now phi x1 also there must be a free field here, which gives you this incoming particle and it comes and decays. And let us now look at x1 to x2 what is happening. X1 to x2, there must be the structure of the vertex tells you that there must be two fermion lines. So there must be two fermion propagators. And you will see that there are fermion propagators. The psi bar x1 contracts with psi x2. Okay? And psi x1 contracts with psi x2. Here you can put an arrow, but it doesn't make sense because ultimately it is doing only. So you can get rid of this. You can think of this way. So this is the diagram. This is fine. This is completely fine. Don't need to put arrow here. And this is the diagram that I drew the last class. This is a really only. So this is coming from another term in the Wick expansion. Let us see whether there are more diagrams or more terms in the Wick. So now what we can do is the following. Since we have got this diagram, I will just remove the contractions. Try to contract this in a different way. Let me call this C. And let me contract it in a different way. So here, once again I contract phi x2 to x3. So this is one contraction. Then psi bar x1, psi x2. Another contraction. Psi bar x1 with psi x2. And then psi bar x2 psi x3. This is another contraction. Let us see what this corresponds to. So here also what we have is the following. Yes. X1. So x1 you can see that there is a free field scalar field at x1. This is the scalar field. And then where are other particles? Psi x1 also is free. Very good. So psi x1, what will happen? So at this point, when the particle is coming, two particles will be getting created, right? Particles are getting created. So what particle can get created from psi x1? Positron. Okay. And so this is done. And then there is another field, there must be another free field, that is psi bar x3. Okay. So let me call this as x3. And what is the particle that can get created from psi bar x3? Electron. It's done. But there should be one more vertex, which is x2. We call this as x2. And you can see x2 to x3, there is a propagator, scalar field propagator. Okay. What about x1 to x2? x1 to x2, you can understand that if there is a positron getting created, there must be electron getting created at this point. So what should this be? This should be psi bar x1 contraction with psi x2. Psi bar x1, psi x2. See, that term is there. So this is the electron propagator. And now, so this is psi bar x1. At this vertex, there should be another fermion line, and so is this vertex. And there must be some contraction between x2 and x3, some fermionic field contraction from x2 to x3. And let us search for that. There must be some term there. Psi bar x2 to psi x3 contraction. So what do we have here? Huh? Here there should be an arrow, and let me just check the arrow. Psi bar x2 to psi x3. Yes. So psi x3, from here something should get destroyed. So that is the electron is getting destroyed. That is psi x3. Therefore the arrow direction should be like this. And psi bar x2, there is psi bar x2, so electron is getting created. So this is the diagram which corresponds to this expression. Once again, you can see that this is not a fermionic field. So this is quite an interesting diagram. Scalar field is coming, it is decaying, and at this point, again, there is an exchange of a scalar field. Particle is going like this, and again they are combining and so this particular is term in the expansion in this expression is 3 corresponds to this Feynman diagram. So we have obtained 3 Feynman diagrams.
Sir?
Yes.
At x3 there is a electron positron annihilation.
At x3.
Yes. Yes.
This is not an electron positron annihilation. See, this electron is coming here. And
No. Okay.
This is the x3 point. This point is x3. This point is x3. Okay?
Okay, sir.
Let us now look at another possibility. Let us call this term as B and see how can we contract that to get any other diagram. So once again, we contract phi x2 to C. You may ask that why are you not contracting phi x1 with x2 or phi x1 with x3? But those will give rise to this same diagram. That is why we are not contracting phi. We are always contracting x2 to x3. But all other permutations will give rise to the same diagram. Okay, we have contracted now this with this. Let's see what else can we do. Psi x2 with psi bar x3. See, from this diagram you can understand something. If there is a diagram with positron, there has to be a similar diagram with an electron. So there should be another diagram where this arrow will be there, but you reverse all these arrows. Let's see whether you get that diagram on. Okay, so I have contracted psi x2 with psi bar x3, and then you can contract psi x2 with psi bar x3, and then you can go psi x1 with psi bar x2. Let's see what this diagram is. This is D. This was C. This term. What is D? So we have x2 to x3 contraction once again. At x1, you have this phi x1, you have this one, and then psi x3 is this is a free thing, free field sitting there. So let me call this as x3, and there is some particle that is getting created at x3 from psi x3, so it must be a positron. The arrow is reversed. Take this as x2. X2 to x3 there is a scalar line, and at x1 there is a psi bar x1, so it must be an electron. This and from x1 to x2 you can see this. There must be a fermion beam. You can just find it there. So this is the diagram which corresponds to this term. Okay. So already we have got 4 diagrams. There is only one more left.
How can you understand how many diagrams will be
That you have to play with. You have to play with.
there?
There is no rule. You have to find it out yourself. But nowadays, see, for this kind of interaction is easy to find, right? But if they give you some more complicated interaction, then you will maybe, and if you go to higher and higher orders in perturbation theory, then it will be more difficult. But nowadays, if you are really doing these type of calculations in your research, then there are programs. So if you run the program, it will tell you what are the possible Feynman diagrams, and it will also calculate the expressions for those diagrams. Okay, so there is only one more left. Let me just remove everything from here, because you can see that this is basically combinatorics, all possible permutation. So you have to just be clever enough to find all the possibilities. So the other possibility, which I call as E, is very simple: phi x2 to phi x3 convection, psi bar x2 with psi x3, psi x2 with psi bar x3. So 3 must be remaining, otherwise we will not get a contribution. And what is this one? These are all three fields which will give rise to psi bar minus x1, psi minus x1, phi plus x1, and that is that vertex. So this is this vertex, and this one is, you can just draw it, x2, x3. x2 to x3 you have a scalar field propagator, and x2 to x3 there are fermionic contractions. This is again a loop, not a fermionic loop. It will not contribute to the lifetime. This is this one. So you have yes.
Isn't it a disconnected diagram?
That is what George just now said. It is a disconnected,
Okay.
the disconnected diagram. So this last term is a disconnected thing. So this is x1, x2, x3. Get a loop. This loop and this 3 is disconnected. And you can get rid of those things. This basically you can show that the vacuum, for the stability of the vacuum, all these bubble kind of diagrams, they will give rise to an overall phase, and that phase will get cancelled out. So this will not contribute. So the only interesting diagrams which will give you correction to the lifetime, to the leading order result to the lifetime of this process, are this diagram, this one, and this one. So there are only 4 diagrams that you need to calculate explicitly. So you can already see that first of all you have to apply the Wick's theorem to identify all the possible diagrams. Once you have identified, so the way you identify what are the possible corrections or what are the possible diagrams, you can be imaginative and you can just think what are the possibilities and you can just draw the diagrams by just thinking without calculating. But then you may miss some diagram, and the only way you can find out what you have missed is apply Wick's theorem. And you will notice that you may ask that you are already always contracting phi x2 with phi x3. What would have happened if I had contracted phi x1 with x2 or phi x1 with phi x3? You can basically show that if you want to do that process and contract, you will end up to one of these diagrams. So it will not give you a new diagram. So the way of identifying what are the possible diagrams is to apply Wick's theorem brute force. Then you can identify all the possible diagrams. And if you are clever enough, then you can just, by imagining from your imagination, remove this basic thing, basic vertex. From the vertex, you can actually construct all the diagrams. As I mentioned, see, in the last discussion, I did not calculate anything, but I drew the diagrams. I drew this one and drew this one. And this was just by looking at the vertex. Because it is a third order term, so there must be 3 vertices. So this is x1, x3. Again, the particles are getting produced at x3. x1, the particles coming and getting destroyed. And since this is a vertex, there is one scalar field line, so there must be 2 fermionic lines. Vertex, same thing happens, and then you get this diagram. And same is true for this diagram. And other 2 diagrams also you could have created just from this very basic vertex that you have. And the same thing you can actually establish by calculating, by using the Wick's theorem, and by making the expansion, you will get all these diagrams. Now, if you want really to calculate all the diagrams, so you can see that it is a very long procedure. You have to calculate each of these diagrams, the expressions for each of these diagrams, get the correction to this basic vertex. The leading result that I have calculated, in order to calculate a correction, you have to calculate all these diagrams explicitly, which we shall do, but it will take some time. So what I shall do today is the following. See, as I mentioned, for this diagram, you can just plain and simple apply the Feynman rules, because this rule you already know. You can just apply the Feynman rules that I derived already yesterday, the rules for the external lines and the propagators, and you can write down the amplitude for that diagram. But for this diagram, you can again apply Feynman rules, but you see that there is an extra rule for the Feynman rules. And let us see this diagram today. So, you can remove these things now and keep the diagram on the board. So let us look at this. This is what we have. And now you can just plain and simple apply the rules. So basically, I call this as x1, x2, x3. Then this will be so this is 5 x2, 5 x3, and you know what this is? It's basically I delta x. Okay. So this is this one. Then you have these things. This is nothing but psi. I call this as say electron. So this electron is getting created here. So this is basically psi bar x1. Electron is getting annihilated here. So this is psi 2 contraction. Similarly, positron is getting created. Psi x1, psi bar x2, and then there are three particles. There will be a contraction, sure. Contraction, and then there are three particles, phi at x1, and psi bar at x3. Now you can immediately see that you can, if you want, you can put indices and everything, because these polygons will have these spinor indices. These are basically column vectors, right? And therefore you can here take indices and all that. So you can put this as alpha, beta, and this is alpha, and this you can already this is how you can put the labels to this. And you can immediately start writing this. You already know what it is. You have to sandwich this between BK and electron and positron. But what about this one? This, we know that this is basically a fermionic property. This gives you I SF alpha x1 minus x2. This one fraction. But this is what? This is I bar with this. These are basically fermionic, anti-commuting. So this is also a propagator, but this is this. So since this is I bar with psi, this will give you minus I SF beta alpha small. And that is the minus sign. So now you can just put in all these expressions. You know all these expressions. You can put their integral forms. You can perform the Fourier transform and things like that. But the important thing is that it's coming here. This minus sign is due to the Fermi loop. So whenever you see a fermionic loop, and you want to write down the expression for that Feynman diagram, the amplitude for the diagram, just write down everything, all the propagators with the proper labelings, and just after writing everything, just put a minus sign. This is a Feynman, and this is coming from this. So for a loop, it is very easy to derive. Just see the extra minus. So what we shall do on Monday is something is just look at any one of the diagrams. For example, I shall just take this diagram and try to calculate the amplitude for this diagram. That we shall do on Monday. And then we shall straight away, after this doing the calculation of this diagram on Monday, then we shall straight away go to the discussion of quantum electrodynamics. And that will finish the course. At least for the time being, it will finish this course. So do you have any questions at this point?
So why are you giving those indices alpha, beta?
Because Because these are basically what? These are basically, this phi is a column, right? This is spinner.
Yes.
So spinner, there are components. Psi bar is a load.
Okay. Okay.
So there should be components, right?
Yes, sir.
That is why I'm putting some labels there. But see, what I wanted to show you is that derivation of this minus sign for the fermionic group, and that is independent of whether you put some alpha or beta here. You don't need to put alpha beta here. But this minus sign is due to the anti-commuting nature of this psi bar and psi. Psi with psi bar contraction is the propagator. Psi bar with psi is also the propagator, but with a minus sign. So this is how you can draw the diagrams, the Feynman diagrams from the mixed here. And you can also look at scattering processes. We are discussing basically the decay of a real scalar field, part of a real scalar field. But you can look at scattering processes also from this U power type of interaction. And that scattering you will only get at second order in perturbation. Second order in perturbation theory. So this will give you the scattering of two particles. For example, suppose you have an electron that is coming here, and then suppose it is electron-electron scattering. So what kind of diagram you can have? So will be at second order. So this is the scattering of two electrons by the exchange of a real scalar field particle. And then you can have another diagram, for example. This, by the way, is called a this is called a T-channel diagram. I will just look at it. It's called a T-channel or U channel. I will just check it. Anyway, but that I will tell you when I do QED. But then you can have another diagram here. You have something like this. So these are the two possible diagrams for electron-electron scattering at the exchange of a real scalar field. You can also have the scattering of electron and positron. What will that look like? This is a S channel. This is simply S channel. So this is electron and positron exchange something. This is a scattering process for an electron-positron incoming particles scattering and electron-positron. And so on. You will have maybe another possibility, another diagram for that process. But all this scattering of electrons or electron and positron, this will be at second order in perturbation theory because you see that there are two vertices. And this will also be all these scattering processes are basically taking place due to U-like interaction that you have put in the theory. So this we shall discuss in great detail when we discuss QED, but for the time being, we can also discuss such scattering processes using this U power interaction, but we shall not do it with U power. We shall straight away do it with QED.
So U power interaction was uncomplex.
Psi bar, psi, phi. Yeah.
So, why is it called deploy?
Because Yukawa gave it first. You will get that potential. You will get it here. You can show that you can calculate the potential for this kind of a interaction, and it will be precisely of this e to the power of minus mu r form, mu r by r form. You'll get that. Okay, so online guys, do you have any questions?
No, sir.
If not, so let us stop for today.